Welcome back to the NMR Challenges series. In the previous video, I provided this NMR challenge for you, and today we are going to explain the solution step by step. If you have already solved it, then you can match your answer by the end of this video. So let's start today's NMR challenge.
This is our fourth NMR challenge. So while determining the structure of this organic compound, we are going to follow all those steps which we learned in the last videos. So first we will calculate the index of hydrogen deficiency, then we will look 1H NMR, and after that we will look 13C APT NMR. Before solving this problem, we are going to revise all those steps which we are learning since beginning, and we will revise chemical shift value for 1H NMR and 13C carbon NMR as well. This is very important to keep revising because this practice will make you perfect. And here are those steps. So first step is calculating the index of hydrogen deficiency, which is also known as degree of unsaturation, and this is the formula. So this formula is 2 multiplied by number of carbon atoms plus 2 plus number of nitrogen atoms minus number of hydrogen atoms minus number of halogen atoms divided by 2. So the value gives number of pi bonds or rings, or it could be both. If this value is equal to 5 or greater than 5, then we can blindly say that it has one benzene ring, and this benzene ring will correspond to the 4 value because it has 3 pi bonds plus 1 ring. Then we will see 1H NMR, and as we said that number of signals is equal to the how many types of protons are there. Splitting patterns will give us information about the number of neighboring protons or substitution pattern on the benzene ring. So here is the splitting pattern formula, n plus 1, where n is equal to the number of adjacent protons which are equivalent. And for determining the substitution pattern on the benzene ring, we should also know the J coupling value. So we will learn when we will have those kind of problems. So here we are just focusing on the aliphatic types of compounds so far. And 1H NMR chemical shift values is also very important to understand shielding and de-shielding of the protons. As I told you, primary carbons, hydrogens coming in the shielded region from 1 ppm to 1.2 ppm. Secondary carbon hydrogens are slightly de-shielded as compared to the primary, and tertiary hydrogens are slightly more de-shielded from 1.4 ppm to 1.9 ppm. And we also learned that when methyl is attached to the ketone, then it comes from 2 ppm to 2.6 ppm, and it is quite similar value for methyl attached to the benzene ring, such as in toluene. So it is also coming in the same region. Acetylene protons is slightly de-shielded as compared to the methyl attached to the aromatic rings. It comes from 2.5 to 3 ppm. This is very interesting value. When oxygen attached to the carbon, then hydrogens are coming around 3.5 to 4.5 ppm more often, and it could be higher also, but usually you will see in this range. And when it is attached to the nitrogen, then it can come from 3 to 4 ppm. We also learned that hydroxy and amines protons are acidic, therefore they can undergo exchange from one molecule to another molecule, therefore their values are not fixed, and it is coming from 1 to 5 ppm. The aromatic protons comes from 6 ppm to 8.5 ppm, sometimes overlap with the alkene protons. This depends on the nature of the alkenes. Aldehyde protons comes from 9.5 ppm to 10.5 ppm, but carboxylic protons always comes after 10 ppm to 13 ppm, and it is slightly broader signal. So we should remember these values because it is very important to determine the structure of the compounds. Then the third step is 13C APT NMR. So we will look 13C APT NMR, and we know that this NMR gives all kind of carbon signal, but in 13C depth NMR we don't see signal for quaternary carbon, the carbon which doesn't have any hydrogen. It also tells us how many types of carbons are present in a molecule. And we also learned that methane and methyl peaks are 180 degree opposite to quaternary carbon and methylene carbon. So in this spectra which we are going to show here, the quaternary carbon and CH2 signals coming in the upward direction, or we can say in a positive phase, and methane and methyl carbon are coming in the negative phase. But remember that when you are solving in MNOVA or any other software, then you can change it. You can change this phase by yourself, and then it could be opposite. But here the NMR which we are looking, in that case we are following this pattern because those NMRs are presented in this way. It is also important to remember some of the chemical shift values for carbon. So here are the some chemical shift value for the carbon. When it is primary, so it is coming up to 35 ppm. When it is secondary, it is slightly de-shielded. Tertiary is coming maximum 55 ppm. When it is connected to the oxygen, then it comes from 50 to 70 ppm more often, but it could go to 90 ppm depending upon the structure. Acetylene carbon comes from 70 to 90 ppm, and benzene carbons comes from 110 to 170. These values for the functional groups is very important to remember. Ester comes from 165 to 175 ppm, but amides could be slightly lower than ester. It can be from 160 to 175 ppm. Carboxylic acid is slightly higher from 175 to 185 ppm. Aldehyde always coming in highly deshielded region from 190 to 200. Therefore, it is easy to distinguish between carbonyl carbon from ester or carboxylic acids. So after revision, now we are ready to solve this challenge. So first we will calculate the index of hydrogen deficiency, or also known as degree of unsaturation. The formula is 2C plus 2 plus nitrogen minus hydrogen minus halogen divided by 2. So there are 9 carbons multiplied by 2 plus 2 plus 0 nitrogen, 12 hydrogen minus no halogen divided by 2. So it would be 4 degree of unsaturation. Since 4 degree of unsaturation is there, so we can say that there is a benzene ring, and benzene ring has 3 pi bond and 1 degree of unsaturation attributed to the ring. Therefore it is equal to 4. So now we have benzene ring in the molecular structure. So there are 6 carbons already occupied by the benzene ring. Now 3 carbons left over. So we have to look 1H NMR. There is a signal at 2.29 and 6.82. So there are two types of proton. Let's call it A and B. 2.29 is singlet and is correspond to the 9 hydrogen, which implies that it could be something like this. But if it is something like this, then benzene ring has 6 carbon and there are 4, then it would be 10 carbon. So which is not possible. And this value around 2.29 also indicates that methyl is directly attached to the benzene ring. Therefore, it cannot have such tertiary butyl group. Now, 6.82 ppm signal is also singlet and it's corresponding to the 3 hydrogen. This gives us information that benzene ring is tri-substituted and it is symmetrical. So it means that there are 3 methyl group which are equivalent. So we have to put this 3 methyl group on the benzene ring. So if you have 3 methyl group, then how many hydrogens are there? 9 hydrogens from the methyl plus 3 hydrogen from the benzene, so total 12. So yes, we can say that there are 3 methyl groups on the benzene ring, but we don't know how to arrange them on this benzene ring. Now look at the 13C APT NMR. From this we can say that this signal is corresponding to the methyl group, and this one is corresponding to CH because it is in the deshielded region, and this one is in the upper direction in the positive phase, which indicates that this is quaternary carbon, or we can say that this doesn't have any hydrogen. So this also shows that there are 3 types of carbon. One is CH3, another is CH, and then C. So this C could be substituted carbon of the benzene ring. So let's try to arrange 3 methyl group on this benzene ring. So I will try to make this molecule symmetrical. If I put the 3 methyl group in this way and draw the plane of symmetry, then this is A type, this is also A type, but this methyl will be different. So this have 2 types of methyl, not one type, and same 2 types of aromatic hydrogen. One is this one and another is this one. So this cannot be the correct structure. So let's try to draw another symmetrical structure. What about this one? So if you draw the plane of symmetry, then we can say that this is similar to this one and this is also similar to this one. So there are 3 methyl groups and all are equivalent. So it will show only one signal. So we will get only one signal for the 3 methyl group. But what about the aromatic protons. If you see, all these aromatic protons have same chemical environment, so 3 hydrogens will have the same signal. So it means the correct structure is this one. Let's try to do the back testing for this carbon NMR and try to assign signals to each carbon. So this signals belongs to the methyl group, this one belongs to this carbon which having the hydrogen. So 100, this 27 ppm, 127 ppm belongs to this, and 137, which is quaternary carbon, is belongs to this carbon having methyl substituents. After interpreting 1H NMR and 30C APT NMR, without any doubt we can say that this is the correct structure of the given molecular formula. And here is the NMR challenge for you. I am sure you can do it if you follow all those steps which we learned in this video. And if you manage to solve it, then don't hesitate to post your answer in the comment box. I will disclose the answer in the next video. So don't forget to subscribe my channel. We will see you in the next video. Thank you very much. Take care. Bye bye.